Hello everyone, welcome back. I hope you had a great weekend. Today's lesson is going to be lesson 222, day 1. We're going to talk about transformations of lines. We've been talking about transformations of parabolas, absolute value, rational functions, cubics, square root functions, but we have not talked about one of the most basic functions of all, and that is the linear function, what makes lines on a graph, and how do we take those lines and move them around on a graph like we have been with the other functions. So we're going to see that today. We're going to start off with a little bit of review for equation solving and factoring, because that stuff is going to be on our upcoming test here soon. So we want to make sure that we're keeping that stuff fresh in our minds. We're going to learn what the graphing form of a line looks like, and we're going to understand what the parameters A, H, and K do to the line. All right, and then we're going to finally write some equations of lines given information about transformations and slope. Okay, so let's start off with our review here. For today's review, we're going to solve an equation and use the factoring method to do it. So we've got an equation here, it's set equal to 0, which is nice, and we want to figure out what values of x make this thing true. So we're going to use factoring to help us with that. All right, so I'm going to start by drawing my box and diamond. So remember, factoring uses the box and diamond method. There's my box, and I'm going to go ahead and set up my diamond here. And remember, when we factor, we take that x squared term, it goes in the upper left-hand box. We take the constant term on the end, and we place that in the lower right-hand box. Now this middle term, negative 6x, that is going to be split between the two remaining boxes, but to figure out how we're going to do that, we use the diamond to help us out. Now we know that these two boxes, we want them to add to be negative 6x, and then we want them to multiply to be whatever this diagonal multiplies to. So if I multiply the filled in diagonal, we'll get negative 40x squared, so we want our blank diagonal to do the same thing. So we need two numbers that multiply to negative 40 and add to give us negative 6. All right, so you might need to think about it, do a little bit of trial and error, but don't give up. All right, so the two numbers that are going to work here is going to be negative 10x and positive 4x, right? Negative 10 times 4 is negative 40. Negative 10 plus 4 is negative 6. So this is the combo that we are looking for. So I'm going to plug those into my currently blank diagonal here. So I got negative 10x and 4x. It does not matter which order you put those in. So now we start working on the outside dimensions here. So remember, to get an x squared, we would need x times x. Okay? And then x times 4 will give us a 4x, and x times negative 10 gets us a negative 10x. And then negative 10 times 4 gives us the negative 40 in the bottom, which is what we wanted. Now our two factors should be visible. So I'm going to take the top here, which is x minus 10. That will create our first factor. There we go. And our second factor is x plus 4. And remember, this is still equal to 0. So this equation that we have written here is the same as the equation that we started with, but this is much easier to solve, right? Because I can use the zero product property to help me out with this. So if I take each of my factors and set them equal to 0, such as the first one, x minus 10 equals 0, that becomes very easy to solve. I can draw a line if I need to, but I think most of us are getting to a point where we can solve this in our heads now, and we can figure out that this is just going to be x equals 10. We do the same thing with this one. I take x plus 4 and set it equal to 0, solve, and we find x equals negative 4. So if I were to take either of these numbers and plug it into my original equation here for x, I would get a 0 on the output. Okay? So these become my solutions. Okay, two of them. Quadratics always have two. Don't forget that. All right, next equation here. We've seen this one before, but it's been a while since we've worked one of these out, so I want to go through it with you one more time. Again, just trying to get some of those older things that we haven't seen in a while fresh in your head, because some of those older things tend to pop up on the test over and over again. They don't go away. All right, so we've got an equation with fractions in it. We're going to clear those fractions using cross multiplication. So I'm going to take these top parts here, these expressions, I'm going to make sure I put those in parentheses like this, and then I'm going to cross multiply. And what that means is I'm going to take 2x minus 3 and I'm going to multiply it by the 3 down here. So we end up with 3 parentheses 2x minus 3 equals, and then we do the other cross multiplication over here, so we're going to do 4 times 3x plus 5. Oops. There we go. And what we end up with, what cross multiplying does for us, is it clears out those fractions and gives us a nice linear equation to work with here. So I'm going to draw my line, and I'm going to start breaking this thing down. So the first thing I want to do is I want to get rid of those parentheses that I started with. I know it's kind of ironic. We put those in there, and now we want to get rid of them, but our x's are trapped inside of them, and if we want to get to those x's, we have to clear the parentheses. So we're going to use distribution to get rid of those parentheses. So I'm going to distribute the 3. All right, so 3 times 2x is 6x, and then 3 times negative 3 is negative 9. All right, so the parentheses are gone there. We're going to do the same thing here on the right hand side. So I'm going to distribute the 4. So 4 times 3 is 12x, and then 4 times 5 is 20. All right, so now it gets a little bit easier. We start to see there's no more parentheses, no more fractions. So now our goal is just to get all of the x's on one side and everything else on the other side. Okay, so I'm going to put my x's on the right hand side. Okay, so I'm going to move the 6x over to the right, and to do that I'm going to do the opposite here. So I've got minus 6x. I'm going to do the same thing over here, so minus 6x. So working left to right, these 6x's will cancel, so the only thing left is a negative 9. And then here, 12x minus 6x is 6x, and then I still have a plus 20. Okay, so remember, whatever you do on one side, you have to do on the other side, and to move anything from one side to the other, you need to do the opposite. Okay, so now I'm going to move this plus 20 over here with the negative 9. So since it's a plus 20, I'm going to subtract 20 from both sides. Okay, and so I get negative 9 minus another 20, so that'll be negative 29 equals, the 6x comes down and the 20s cancel. So now this is all that's left, and our last step here is going to be to separate the 6 and the x. Currently those are attached to each other by multiplication, so 6 times x. So to separate that, I'm going to have to divide by 6. Okay, and there the 6's will cancel, and so I'm just going to leave it in its fraction form, and that's perfectly fine. So I'm just going to say negative 29 over 6 equals x. And you're more than welcome, if you want to put that into the calculator and get a decimal version for that answer, that's fine too. It just doesn't work out to be a nice number. So I prefer fractions. I like fractions. I think they're numbers just like any other number, and so this is just fine for me. All right. Okay, so hopefully that refreshes your memory on some of those equation solving skills. So we're going to continue on here with the primary objective of our lesson, that is to learn about lines. Right? We've learned about lines since 8th grade, so there's a graph of a line, and the graph that I'm showing you here is what we call the parent function. So this is a line before we do anything to it, right? We have not reflected it, we have not moved it left or right, we have not moved it up or down, we have not stretched it, we haven't done a thing to it. This is what it is, and its equation, the most basic line there is y equals x. Okay, and its graphing form looks very familiar compared to all of the other forms that we've been looking at. And we have a times x minus h, and we have a plus k on the outside. You'll notice what's missing here is the 2 or the 3 that we normally have, like on a quadratic or a cubic, and when you take that exponent away, that's what makes it a line. So this is the equation that we're typically going to want to write for our lines. You may be more familiar with this form, right? Mx plus b. This is another very popular form of a line, but this one is nice because it shows us the transformations on the line. So this is the one that we're going to be focusing on today. All right. So what I want to figure out again is, what does a, h, and k do to our lines? And there's not going to be too much surprise here. A, h, and k do the same thing to the lines that they did to the other functions, but there's some other things to explore as well. So we're going to go to Desmos, and we're going to give it a try here. And I have the parent function of my line already typed in. So I'm going to just type in. I'm going to type in a line here. Let's go 3 parentheses x minus 2 plus 1. Okay, and let's do this. Let's say we put these all defaults for just a minute, right? So like normally a default for A is 1, right? So if we don't stretch it or compress it, A would be 1. And if we don't move it left or right, then H would be 0. And if we don't move it up or down, K would be 0. So now you see my blue line has landed right on top of my red line. There is no difference, and we can see a place for each of those parameters to go in. So let's see what happens when I adjust this number on the end, right? This is our K value, and we remember from our previous functions that the K value moves things up and down. All right, so let's say I put a 2 in there. And you can see over here in our graph, right? This is our parent graph, this is where it started, and then when I did a +2, it moved it up 2 units. So it just shifted it up 2, which is what we expected to happen. Okay, so now let's see what it looks like when we horizontally translate here. So I'm going to go, let's say we want to move it to the right 3, right? So then we would have a -3 in the parentheses. So I'm going to go -3, and there you go. So you can see it moving to the right 3, which looks a lot like it moved down 3, but that's the weirdness of lines, right? So it did move to the right 3, but it also looks like it moved down 3. So there's some weirdness with those lines going on there. Let's put that back at 0. Now let's experiment with A a little bit. So remember, 1 is the default. So remember, stretching a line means putting in a number bigger than 1. So let's try and put in 2 and see what happens. And you can see what it adjusted there, right? So it looks like it got steeper. Right, so this line got steeper. If I put in a 3, it gets even more steep, right? 6, steeper. So let's try a number in between 0 and 1 and see what happens there. It's like if I did a 0.3, you can see it got less steep. So what this number A is controlling is the slope of the line. So if you recall from Algebra 1, slope controls the direction or the steepness of the line. So what we interpret as a vertical stretch actually adjusts the slope of the line. So this number out front is our slope, our rise over run. Okay, and then these numbers control the vertical and horizontal position of the line. Okay, so locator point, just something else to quickly talk about here. Locator point still 0, 0, just like it was for the other functions. All right, so let's go back here and let's jot down some things. So remember, A controls our slope / steepness, right, / direction of the line, right? These are all good ways to describe it, but that A value is very important. Slope is one of the most important pieces of information you can have about a line. H controls horizontal translation, like left and right, movement, and K still controls our up and down. And of course, if you want the line to go the other direction, you would reflect it by putting a negative in front of the A value, just like you would for the other functions. Okay, so let's look at a problem that we might do. All right, so it says use the graphing form of a line to write the equation of a slope of a line with a slope of 4/5. So they're giving us a slope. Remember, so that's the equivalent of giving us an A value, right? We figured that out with our experimentation in Desmos, and it has to pass through the point 3,9. And we can guarantee that it passes through the point 3,9 by making 3 our H value and making 9 our K value. And I give you that hint here, right? Use 3,9 as your new locator point. So no problem. So we're going to start with the general equation of our line. So y equals A parentheses x minus h plus k. Okay, so I'm going to take my slope that they gave me and I'm going to put that in for A. So I've got y equals 4/5. All right, so just put that in for A, and then I've got minus h. All right, so remember we're going to do, our h value is going to be this 3, so we're going to say it moved to the right 3. So to move right 3, we need an x minus 3. And then our k value, right, we're going to pretend that it moved up 9, so we're going to say plus 9 on the end. So this would be a line that passes through the point 3,9 and has a slope of 4/5. Okay, so not really much different than what we've been doing with the other functions. It's just there's a new tie-in, a new link between the stretch and the slope when it comes to lines. Okay. All right, let's try one more here. So we've got a line that passes through these 2 points. We need to determine the A value using a slope formula and then write the equation of a line using either of the 2 points as our locator point. No problem. So if you recall from Algebra 1, the slope formula looks like this. We have y2 minus y1 over x2 minus x1, right? And remember, the change in y represented this thing that we called the rise, and the change in x's represented this thing that we called the run. Rise over run, and this is how we calculate the rise. This is how we calculate the run, okay? So let's do that calculation real quick. So these are the two y coordinates, right? So here's my point. Let's call this y1, and this will be y2, right? So y coordinate, y coordinate. So if I do y2, that's -2 minus y1, which is 5. There's my calculation for the rise. I'm going to do the same thing for the x's, right? So we'll say this is x1 and this is x2. So x2 is 8 minus x1, which is -1. And then we just straight up do these calculations in the top and the bottom. All right, so -2 minus 5, that's a -7. And 8 minus a -1 is a +9. There's my slope. So we'll say there's my a value. Okay. So I'm going to start writing my equation. Remember our blueprint for the graphing form: a parentheses x minus h plus k. And so my a value we just determined was -7 over 9. And then we have x minus our h value here. And we can pick either one of these 2 points. It doesn't matter which one. We'll get the same line either way. That's a really cool thing about lines. So I'm going to pick this one, the x2, y2. So I'm going to say x minus 8. And then -2. There's my equation. Okay. Another equation you can get if we used the other point, you would have the same slope, right? But you would use this one. So this would be x minus a -1, which would turn into x plus 1, and then you would have plus 5 on the end. Either one of these represents the same exact line. All right, guys, that's it for today's lesson. Good luck. Try the practice problems and let me know if you have questions in the Zoom chat. Have a great day.